Okay, today we will talk about FPGA. So it's very expensive to build a application-specific circuit design. You need to hire a lot of engineers to do that. So it's more practical to use a FPGA board to try your design. And then after you feel everything is good on your design, you can fabricate your design into some circuits. So we need some reconfigurable platform to debug and test our designs. Then we need FPGA. FPGA has the capability to reconfigure its components to implement any digital logic function. Partial reconfiguration allows a part of the FPGA to be running, and another portion can be reconfigured. FPGA also have some analog circuitry features, including some programmable digital to analog converters and analog to digital converters. These components can help you to handle the analog signals. For example, if you want to deploy a sensor, a temperature sensor on your design, the sensing of the temperature part is, of course, some analog signals. And then you can convert these signals into some digital digital bits to see whether these bits are larger than some threshold value, and then to do something. By the finite state machine we introduced in our previous class. So with all these sensors, control logic, and reconfigurable components, we can have a system on chip, so-called SoC. Your mobile phone is just a SoC because your mobile phone has multiple sensors and a CPU and even a GPU. So this is the example, simple example of FPGA board. It has a n times n array of unit cells. Each unit cell is a memory element. You can store a part of the truth table inside this element. By adding more memories, by adding more dedicated multipliers, CPU cores, we can have more and more advanced FPGA boards. So for the memory part, we can have a single port or dual port RAMs. Dual port RAMs can support concurrently read and write. We can also have some FIFO, some queues, and we also have some ECC, which can correct errors on these memory components. Now we have a lot of deep learning applications. So we need a multiplier, accumulator, and some dedicated arithmetic logic units, ALU. So these are very common on the state-of-the-art FPGA board. Sometimes in order to achieve high performance, we also have embedded processors. For example, some FPGA board has some ARM core to process those general purpose regular applications. With those CPUs, ARM cores, memories, and the DSP and the ALUs, you can achieve a very good performance for different applications. You can even synthesize a software core and deploy that on those memory elements of the FPGA boards. So here is a more here is one example with more details of FPGA board. So we have some configurable logic blocks here. Each of them can store a part of the truth table. And then we have the interconnections. Of course, the interconnections are also reconfigurable so that you can connect this part, and this part. Maybe this part. You can connect any two of them, three of them, or four of them. And then we also have some programmable I/O interface. And these interfaces can help you to connect this FPGA board to some other dedicated circuit. So here is one example. You can actually configure this part as a XOR gates, this part as a latch, and this part as a AND gate. So you can actually configure different reconfigurable component on the FPGA board into different functions. The configuration is very simple. You just write the truth table into that part. And then we have also some switches on the interconnection. And by adjusting those switches, you can configure those interconnections. So you can do the configuration even when the circuit is running. You can configure these idle components when the other part of this FPGA board is running. So the configurable logic block consists of some lookup tables for your truth table. So these lookup tables can also be used to implement some RAMs. It also has a part of the for the carry and control logic. So by these components, you can implement very fast arithmetic operations like adders and subtractors. Or you can use them as you can use them to serve as some circuit for the testing. You implement something in the lookup tables and you need to do some testing on that. You can also utilize these carries and the control logics. Of course, we have a memory element, the latches, to support the finite state machine, to support the multiple clock operation. So different FPGA may have a different amounts of those configurable logic blocks. Some more advanced FPGA has many of these resources. So some FPGA also contain some wide function masks that can implement 4-to-1 masks, 8-to-1 masks, and 16-to-1 masks. By using these masks, you can connect different part of these lookup tables. So the configuration memories hold the output of the truth table entry here. These are the configuration memories. And then you can use these masks to select one of the entry. So the truth table is actually stored in the memory components here. And then by the masks, you can select one row in the truth table. That's the reason why the mask is very important. So the normal lookup table mode performs only read operation because you only need to look up the tables. And during the reconfiguration, you also need to update the memories here. Then you need an address decoder to enable one row and change the content inside this row. So these smaller RAMs can be combined into a larger RAM array in some advanced FPGA board, but you need those reconfigurable connections. There are multiple types of interconnections, but all of them share some basic components. For example, the most important part is this one. This is so-called programmable interconnection points. So this configuration bit can serve as a configurable latch. If you set it as 1, set it to 1, then A and B are connected. If you rewrite it into a 0, then they disconnected. So it's just a switch. By using multiple parts of the PIP, you can have these structures. You can enable some of them and disconnect some of them to do the routing, to try to connect multiple parts of the lookup tables. So we also have bidirectional buffers, which can use to store both input and output. We have tree-state controls for those bidirectional operations. We have pull down and pull up registers. We also have a multiple latch to improve the timing issues. These components can help you to build a better interface between the FPGA board and some outside circuit. So the most important part here is how to configure the FPGA board. In order to do the configuration, we have an interface. We have different modes. For example, the master modes. The FPGA can actively retrieve some configuration from the memory at the beginning when you power off the FPGA board. All the FPGA board can be configured by some external sources. For example, this is very useful during the partial reconfigurable runtime. When you run something on the FPGA board. And your application may only require some of the components. You can actually reconfigure the other components, idle components in the FPGA board. And in this way, you can prepare for the next application. So we have some standard IEEE standard interface for the reconfiguration and the testing. So here is one example of the interface, boundary scan configuration. So it can be used to configure your FPGA, or it can be used to test some part of your FPGA too. For example, you can use the interface to test the interconnection between the chips on the PCIe. So here is one example. How to do the testing. You have a multiple FPGA board here, and then you can test them by one single boundary scan configurations. Sometimes the configuration of FPGA can be very large. You can naively direct read them from some memories, but you need to pay longer download time, or you can do some compression. So you need to uncompress the data at runtime, and then write these uncompressed data into the configuration memories. So some FPGA also support the partial reconfiguration and the readback. Only change a part of the configuration's memory based on your design needs. So in this way, you can reduce the download time and reconfiguration time. So here is one example of the real FPGA board, which is a Virtex 5. Now it's just a low-end embedded FPGA board. We have dedicated memory, onboard memories here. And we have a multiple reconfigurable component here. We have 1, 2, 3, 4, 5 different reconfigurable components. And this is the resource list. So the most important part is still the configurable logic block. So one single configurable logic block in this Virtex 5 consists of 2 slices. One slice for the logic, the other slice is for the memory. And they connected by a switch matrix. So you can reconfigure this matrix so to implement the different functions by this CLB. So every slice actually contains 4 lookup tables. And the write function masks carry logic and configurable memory elements. The slides used to implement the memory also support to store data using some distributed RAMs and a memory shift. This is enabled by some 32-bit shift register. So this is an example of the slides used to implement the logic. You have more carriers here, more lookup tables, and more masks here. And this is the example for the slides used to implement memories. This is similar to the previous slides, except that now we have distributed RAMs here. We don't have the dedicated lookup tables, but we have distributed RAMs here, a larger memory component. By adding different numbers of reconfigurable logic blocks, you can implement different types of FPGA board, from low-end to high-end FPGA boards. So different FPGA boards have different resources. Of course, if your design need more reconfigurable resources, you need to buy a high-end FPGA board. So this is the layout for one lookup table. You can see that we can actually connect 2 5 inputs lookup table together, and then treat it as one single large lookup table component. It can help you to implement a logic AND, logic OR, which means that you can configure it into AND gate and OR gate. Besides those lookup tables, we also have some I/O cells on the FPGA board. The I/O cells can help you to improve the system clock to output timing and support single data rate and double data rate. Single data rate means each transaction is triggered by the rising edge, and double data rate means each transaction can be either triggered by the rising edge or falling edge. So in each cycle, you can have 2 pieces of data go through the I/O. And this is the layout for the I/O cell. So you can see that the I/O cell here are actually much larger than one single CLB configurable logic blocks. So besides the CLB I/O cell, one FPGA board also has an interconnection network. I believe the interconnection network occupy the largest area on the FPGA board. It includes long lines, double lines, and hex lines. So different lines can support different connections. And the hex lines, of course, is the most expensive line. It can support 3 connections into a switch matrix. Long lines is just the regular lines. It has beginning, mid, and end. So here is the line, the example for lines. We have long lines and double lines. And the hex lines. By hex lines, we can support a matrix here. We can support a matrix here. And on all the lines, the PIP is the most common component. The PIP is the switch. So now we can see that we integrate more and more transistors on one single chip based on the Moore's law. However, now it's really difficult to maintain this trend anymore because of the limitation of process technology. Now we have reached maybe 5 nanometer, 3 nanometer. So it's really difficult to scale it anymore. We also have the power issue. You know, now one simple CPU or GPU may consume 200 volt. The power is a very big problem. So in this situation, FPGA may be a very power efficient and cost efficient solution for your applications. And of course, FPGA also need transistors to build FPGA boards. But we can use some more advanced process technology to implement those FPGA. One example is the 3D integrated circuit. So this is the example of a traditional 2D. You have multiple metal layers for the wires to implement your interconnections. And we also have an active layer for the CLBs. This is a traditional design. By the traditional design, you can see we have a hex line, long line. The line distance become very long, become very large. Longer distance indicate you have a larger resistance and capacitance. All of these factors will be converted into slow speed and long latency. So you can see that if the lines on the FPGA board is very long, then your FPGA cannot run at a very high frequency, and you will eventually have the power problem soon. Now it becomes more and more expensive to design a ASIC design, dedicated circuit. So less and less companies are willing to design the circuits anymore. So people will use FPGA board to implement their design nowadays. So you can see the market share of FPGA board become more and more significant. And on the FPGA board, because of the traditional 2D process technology, 60% area is occupied by the interconnections. So the wire delay, the interconnection dominate the performance of your FPGA board design. We only use 16% for the CLB, for the real logic. With such long wires, we have a more serious reliability problem. For example, the crosstalk. You will get a lot of noise when you're on those long wires on the FPGA board. So one simple solution for all these disadvantages of FPGA board, long wires, 2D process technology is the emergent 3D integrated circuit. Besides one active device layer, we can add more active layer vertical in the vertical direction. We can stack multiple digital parts, analog parts, communication parts, even your connection into a 3D structure. So each layer of this 3D structure can serve as one function unit. It can be reconfigurable internet or a CLB component. So in this way, you just need to connect them vertically, and the vertical distance is shorter, which means that you have a better signal integrity. You don't have a crosstalk problem. The latency on that short wire, it will be very short. Then we have multiple active device layer like this. We can even design some 3D structure for the FPGA board. Now the interconnection or the CLB can be in 3D structures. So you can configure them in 3D directions. Because we add another one extra direction like this. So it provide you larger flexibility and freedom to design your circuit. So here is one example of the 3D integrated FPGA board. We can have a programmable interconnection layer like this. And then we have a bottom CLB layer and a top CLB layer. In this way, we can have a multiple device active layer. But have the same area overhead because we vertically stack multiple layers together. Any question about this? So if you have any question on your project topic, we can discuss in the next lecture. Next lecture, you just need to do the presentation. You don't have to do a perfect presentation. You can bring your questions to the presentation, and we will discuss. After that, I give you 3 weeks to implement your project to see whether it's feasible to do the project. Of course, you can change your topic, but I want to give you 3 weeks to build some important component. Any question about the FPGA and the project?
I have a question.
Yes.
I want to talk about before we're gonna have a final project.
No, that's good. We only have one project.
And that's this one?
Yes.
And we have 3 weeks to implement?
Yeah, no. You have 3 weeks to build some components, and then you need to submit this project maybe at the end of this month. You don't have to finish that in 3 weeks. I just give you 3 weeks to build some components and see whether it's feasible to do the project. Some students may have very ambitious goals, but it may not be feasible to do that. You can use this 3 weeks to try. So if no question, we can stop today. Thank you very much.
If we realize, if we realize that the project is like not feasible, we then after the 3 weeks, like the steps.
You can change.
And then
you can change.
Do it and then submit the project.
Yes.
Okay, thank you.
No problem.